And we can move on to our next speaker, who is also remote, I assume, unless he took a train in the night.
He sure is.
Yeah. Hi, Angus.
Hi.
You have 12 minutes, and Angus is going to tell us everything about Redshift. Everything about Redshift. Go ahead.
I certainly am not going to be able to tell you everything about Redshift calibration, but I will do my best. So thanks very much, everyone. It's a pleasure to be here. My name's Angus Wright, and I'm going to be talking to you about Redshift calibration for cosmic shear. I've got the great privilege today of being able to talk after a bunch of excellent speakers who've already given you a whole lot of introduction to the stuff I'm going to be talking about. So Elizabeth Krause's great review, Yari Davidson's lovely flash talk, and Dan Masters' talk on manifolds. I'm going to begin, though, with a very quick sort of introduction for the non-experts about why Redshift calibration is important for cosmic shear. And I'm going to do this in the most visual sort of way that I can think of. And so this is kind of the thing that we're interested in cosmic shear. You can consider this picture to be the world's smallest cosmic shear survey. We've got a distribution of source galaxies at the back with random ellipticities, and light from those source galaxies travels through the cosmic web, going through similar large-scale structures. And what you end up with is a correlation imprinted on the ellipticities of galaxies on sky. Now, the reason that Redshift calibration is so integral to this process is because what we have is some distribution of sources in the background with some true redshift, with some true average redshift to first order. Now, what happens if we get that redshift estimate wrong? So let's say that we misinterpret the position of these two source galaxies as actually being much closer to us in the foreground at this average Z-est. Now, crucially, the assumptions that we make about the distribution of source galaxies at high redshift or at the redshift that they exist don't change because we make that error. The observed shapes of galaxies on sky at the telescope don't change because we make that error. And so we see the same imprinted signal, but we interpret that imprinted signal as having come from a much shorter line of sight. And that means naturally that we must interpret the universe as having much more structure in it. And so we assume that the universe is clumpier than it actually is in this particular example. So this is why redshift estimation is so crucial in cosmic shear, because we can actually intentionally perform this experiment of performing redshift calibration with a sample we know to be catastrophically biased and watch it directly impact the statistic that we're interested in, which is S8. So what I'm showing here is a plot from a paper that I had last year, which is just showing using previous redshift calibration methodology, so not the machine learning method I'm going to talk about. If we have a calibration data set that is pathologically missing sources at high redshift, we overestimate the value of S8 because of this exact situation. We underestimate the redshift distribution of our source sample, and we lead to overinterpretation of the signal that we're interested in. And so this is bad. And it's bad for two reasons. Firstly, because obviously you don't want biases in your analysis, but moreover, because even if you go to this purple thing, which is using the full calibration sample, how do you know that that full calibration sample is good enough? If your method is sensitive to these sorts of selections, then you have no mechanism of knowing when you've reached a stopping criteria. And so what you need is a method that allows you to be insensitive to this sort of a selection. And that's where unsupervised manifold learning comes in, and that's where we're currently moving with redshift calibration in cosmic shear. So what I'm showing you here is a summary slide showing the redshift calibration procedure that's being done by two of the large-scale cosmic shear surveys that are running at the moment, the DES Y3 and KIDS 1000. And what you can see in the DES is something we've already heard from Elizabeth, which is that you have a couple of SOMs which you have to use because the wide field DES data has fewer photometric bands with different photometric properties than the deep field data that are used for calibration with the actual spectroscopy. And so what you have is two SOMs, and this is a great figure that I stole from Miles et al. Highly recommend you go see this paper. It's really, really excellent. And basically showing that you have this wide field SOM, which is a low resolution. You then define some transfer function that maps you to deep data, and that then allows you to do your calibration. In kids, the situation is a little bit simpler because we don't have differing photometric properties on the calibration sample and the wide field sample, because we have this survey set up that allows us to have 9-band information over the entire survey. And what that means is that I can have a single SOM trained on spectroscopy, which is what I'm showing here, just colored by counts and counts of spectra. And then I can directly map in the wide field photometric shear sources. And then that direct mapping gives me essentially a classification, which allows me to say, okay, these photometric sources belong with these spectra. And then I do a simple reweighting to end up with my redshift distribution. Both of these methods have different bases and have different details behind them, which I don't have time to go into. But fundamentally at their core, they both use a self-organizing map as a mechanism for matching known spectra to wide field shear sources. For the rest of this talk, I'm going to assume that that transfer function in DES is known perfectly and that it's known perfectly in kids as well. So let's move that complication to the side and see what happens. Does this mapping between known spectra and wide field sources using a SOM improve the state of the art with regards to redshift calibration? The answer is yes. So this is the plot that I showed you before, showing with previous redshift calibration in kids, how we were sensitive to whether or not we selected a deeper spectroscopic calibration sample. And the reason that that dependence existed is because if you look at the photometric space, the color space, which I'm showing here by a SOM, colored by the difference between the mean redshift of the entire SOM of all spectra versus the mean redshift of just spectra in a particular tomographic bin, which one is not super important, then what you can see is that there are lots of cells that are pathologically biased. And this is because of the way in which photometric tomography works. Happy to go into that in questions if people are interested. But the important thing is that the reason that this bias exists in the previous mechanism is because there was no method or no metric to be able to flag areas of the color space which have wide field photometric sources in a tomographic bin, but which do not have a corresponding spectrum. Now with the SOM, that determination is trivial. All you do is you populate the wide field sources into the SOM just like you do with the spectra. And what you find is that all of these cells that don't have spectra in them drop out of the sample. What we're doing is we're then throwing away those wide field data, essentially trading precision for accuracy. And what you see is that then the bias that we had when we use different calibration samples alleviates. This is true if you stand back and don't look carefully, because even in the case where you have perfectly representative spectroscopy, the individual SOM cells are catastrophically biased many times. And that's just because of sampling. If you use something like C3R2, this gets better a little bit. So what I'm showing here is the individual SOM cell bias, the training sample mean redshift versus the target sample mean redshift. The individual cells are the dots, the average is the running mean is the line. And the lines here, the shaded regions are showing basically catastrophic bias for stage 3, okay for stage 3, and good for stage 3. And what you can see is that even with perfectly representative spectra, things don't work perfectly. If you use the C3R2 method of uniformly sampling the SOM for your redshifts, for your spectroscopy, things work really, really nicely. But this assumes that you have 100% redshift accuracy. And the problem is that we are in neither of these scenarios. We are in a scenario where we have SPEC-Z targeting selection functions, SPEC-Z success selection functions, and confidence selection functions. And all of these contribute to increasing the covariate shift between the spec sample and the wide field photometric sample. And that's bad. So can we mitigate this bias? Well, the first thing you can do to try and mitigate this bias is to say, mitigating it is difficult, so I'm going to simulate the effect n times with n different realizations of my deep field or spectroscopic samples, and I'm going to use that uncertainty as an additional uncertainty in my calibration, and I'm going to end up with something that encompasses the truth, or at least I believe encompasses the truth. And that's what you can see is being done in the DES with these sample variance factors here, and that's essentially saying that I have to iterate over, or weight over the possible sample variance realizations of the deep field data that go into my calibration when I'm defining this transfer function. And in kids, we simulate over the possible sample variance realizations of the actual deep fields that we draw our spectroscopy from. This only works if you do both photometric noise and the sample variance calculations at the same time, because the two effects on their own don't introduce significant bias. It's only when you combine them that you get this very strong covariate shift, and that's when the things go bad. The way in which we tried to alleviate this further with kids was by combining template fitting, so classical methods, with this machine learning algorithm that we've used in order to further down select some cells that we think are pathologically biased. So you can see here, again, the same figure now for the realistic spectroscopic sample that we had in kids. And you can see I've identified one tomographic bin, which is our worst, most difficult tomographic bin. It's the one between 0.7 and 0.9 in PhotoZ. And you can see that there is a significant trend here. So what we do is we utilize photometric redshift estimates to identify cells that are pathologically bad, and we throw them out. And it kind of works. It works a little bit. It doesn't do anything great, right? And this is a demonstration that if we're going to improve this process, we need to do something more intelligent about the fact that we have a highly non-trivial selection function in spectroscopy. It works better if you have something like C3R2. So this is a shining, a possible light at the end of the tunnel. So this is the current situation with redshift calibration for cosmic shear at stage 3. Both the DES, shown by these data points here, and kids, shown by these 4 data points here, have demonstrated in their various cosmology papers that it looks like our analysis is pretty robust to the various choices we're making in redshift calibration. We're not getting sort of 1 sigma shift because of redshift calibration like we've been worried about for the last few years. But the game isn't over, because what comes next is Euclid. And with Euclid and Rubin. And with Euclid, even if I use perfect photometry, so this is perfect photometry, model photometry used to calculate a SOM, and I'm showing the N of Z per cell, just in this sort of joy division plot. Even in this case, the sampling of the spec Z mean that you get this covariate shift, and you end up with pathological biases that Euclid is not going to be satisfied with. So Henry was quite right on Monday when he said, I'm worried about Euclid, right? That's a very sensible position to take. And we can try our method the best case methods for improving this situation, like we used in stage 3, doesn't help. So we are going to have to generate new methods for the next generation of cosmic shear surveys. This is my summary slide. I'm going to flip back to in a second, because this is the thing I wanted to end with. We are not ready for Rubin and Euclid.
Thank you. I'm not sure if we should thank you or just be very scared. Any questions in the audience for Angus? Not yet. I'll just have a naive question. Do you expect that there is a new kind of methodology that could be developed to address these biases?
Yeah, so Dan actually flagged it in his talk. The possibility of utilizing a combination of clustering redshifts, which use the spatial correlation between the photometric sample and spec Z, in cadence with the individual cells of a SOM, is a really, really interesting idea, and is a really sort of probably the next obvious step. I think that it's fairly clear from what we've looked at already that there isn't going to be any one method that is a silver bullet for stage 4. I think the way in which we're going to proceed, and this is a personal opinion, is with combinations of methods that utilize different strengths. So machine learning that utilizes the unsupervised parameter space, template fitting that utilizes the assumptions that we know about how we model galaxy SEDs, and spatial cross-correlations that allow us to remove color entirely. But it really is a tough game, and it's going to be difficult.
Thank you very much. You have a question from Roberto Trota, who is just asking if you could stratify your SOMs based on what he talked about yesterday.
Yeah, so I mean, I was really interested in Roberto's talk. I think that the most difficult thing is that in order to calculate these particular, oh, I've forgotten the name of them. These statistics that Roberto uses to do his stratification, we need to understand the selection function. And the problem is that the spectroscopic samples that we're using come from tens of different surveys, all with different selection functions and all with different complex mechanisms, different components like the targeting, the success rate, and the confidence rate. And so if we can understand those selection functions, then I think it's doable. But there be dragons.
Okay. Thank you again, Angus.